This video is an overview of the Brio Marble Injection Mold Process Capstone project for the Fall 22 semester at BYU, Idaho. The team members include Rubiel Ramos, the scheduler and task manager, Braden Fodderero, the meeting manager and data recorder, Aaron Loader, the treasurer, and Bill Edholm, the team leader and sponsor liaison. The objective of this project was to encapsulate in plastic a light-emitting PCB using injection molding. One challenge of this project was to choose a material that minimized voids and shrinkage in the marble and allowed the PCB to survive the injection molding process. After research into the injection molding process and a concept generation activity, the team narrowed down their concepts to 4 mold designs. Using SolidWorks, the 4 mold designs were modeled and then 3D printed. The 3D printed molds were used for initial prototyping with hot glue and a balloon light in place of the PCB. After the initial round of prototyping, the overmolding process was selected as the concept to progress to the second wave of prototyping. The final prototypes were milled by a manufacturing lab TA out of steel, and pins and liners were press fit into the mold to assist with the injection molding process. Two materials were selected for testing: acrylic, which was found to have an optimal mold temperature of 176 degrees Fahrenheit and an optimal material temperature of 518 degrees Fahrenheit, was found to crack easy and produce voids. Polycarbonate was tested and found to have an optimal mold temperature of 225 degrees Fahrenheit and an optimal material temperature of 500 degrees Fahrenheit. Polycarbonate was found to have less cracking because it was a stronger material but still had voids. The team also tried multiple mixed materials, including a 25% polycarbonate and 75% acrylic mixture, a 50-50 mixture, and a 75% polycarbonate, 25% acrylic mixture. The ideal mixture was found to be the 50-50 mixture with an optimal material temperature of 500 degrees Fahrenheit and an optimal mold temperature of 215 degrees Fahrenheit. Product testing included water testing, drop testing, light transmissivity testing, and compression testing. The PCBs were not finished by the end of the semester, so PCB testing was unavailable. But for more insight into how the PCBs would react to the injection molding process, 3D printed models of the PCBs were used in testing, but the results were inconclusive because the 3D prints melted due to the high material temperature. Our team was able to successfully design a process for injection molding over and fully encapsulating a light source while minimizing shrinkage and voids. We wanted to thank Tyler Wigren, our sponsor, for the opportunity to take part in this project and to learn a lot about injection molding. We also wanted to thank Brother Seth Martin, our project mentor, for his help on this project.